make sure I hit all of them.
Okay.
Where it ends up is where it ends up. In this particular case, since I'm pointing in all directions, it sort of loops around.
Okay.
But I could have done A plus D plus C plus E plus B if I wanted.
Mhm.
And ideally, if I'd drawn this perfectly, I would have gotten the exact same answer.
Okay, gotcha.
The same way with regular math, 1 plus 2 equals 2 plus 1. The order does not matter.
I don't know if you said it, but how do you know which one to compare it to? Would it be the closest one?
Compare which one to get this?
Yeah.
It depends on what I gave you. In this particular case, I told you what this represented, the magnitude of this, and so that's why I compared that to this. I could have told you that was 3 newtons, in which case this would be much smaller.
Okay.
All right, what we're gonna do next is we're gonna take a small little break, because this is a marathon session. Come back, we're gonna do a pre-course assessment, and then after the pre-course assessment, we're gonna talk about forces in more detail. In enough detail that if we do it right, we'll dream about them. We'll do it wrong, we'll dream about them, one or the other. Anyway, let's take 5. And if you have Dave Brubeck's tune running through your head right now, good on you. Well, I hope you had fun with that. I think that's the right word. All right, so let's talk about forces in more detail. This is sort of the help with the memory is it's sort of a checklist for the forces we'll be faced with, at least for the first number of chapters. So the first F stands for friction. And the symbol that I will be using for friction is what I refer to as the Baruch F. Baruch F. It is just the fancy lowercase f for the lesser curls. This T is for tension, and I use F with subscript of capital T for tension. I used to use just a capital T for tension, and you can get away with that for a while, but we eventually get to a chapter where we need to use period and tension, and the symbol for period is a capital T. So I'm trying to use F subscript T for tension, and so just so long as I don't have to change my mind later on. O is for other. And the symbol really it's problem dependent. So I just put problem and depth, problem depth. It's a problem dependent thing. I needed a vowel, and it really does depend upon the wording of the problem. W is for weight, or in general gravitational force. Weight is a specific example of gravitational force. We will be dealing with weight up until chapter 9. I think 9 is when we'll deal with a more generalized version of it. But the symbol for weight is a lowercase w, at least the one I'm using. And for general gravitational force, I use a capital F, the lowercase g subscript. And N is for normal force. And the symbol I use for normal force is a capital Y. Now the reason I use a capital Y is because my high school physics textbook used a capital Y, and it's sort of stuck, and we don't use capital Y for anything else. If you look at uppercase, lowercase, our alphabet, and Greek alphabet, we have 100 characters. There will be some repetition. Any questions? At this point, I would expect handwriting questions or,
For other. Yeah, what's the O symbol?
what is this?
Yes.
Prob-dep, problem dependent.
And if we see a lowercase w or an F with a subscript G, that could be weight or gravitational force, like
Yeah,
either one.
I typically use weight when, we'll get into the requirements of how to distinguish between the two. I typically will use weight and up until chapter 9, at which point I'll introduce gravitational force, the generalized form. But weight is a specific case of the gravitational force.
Okay.
So that's why they're sort of lumped together.
What
Yes,
if it
let's-
says on the weight?
What is this?
Yeah.
Oh, it's supposed to be gravitational force, but I left 2 letters out. There, that's much clearer. Gravitational. Now, for those of you who might be concerned for future generations, I will say that when I taught elementary school, I did try very hard to write as neatly as possible. And when I started teaching at community college, I thought, I don't have to write neatly anymore. Apparently, that was not a valid assumption. Maybe it's just, I don't write neatly anymore. All right, requirements. In order for friction to exist, there must be desired relative motion. So if I have 2 objects that are touching each other, one of them wants to move at a different velocity than the other object that it's touching. Desired in the fact that it doesn't actually have to move. You can still have friction. I will do plenty of examples, just sort of setting up a foundation of words. Tension, the requirement is a tight, or the reason they use taut here, taut rope, chain, string, whatever happens to be pulling. For some reason, I crammed it into a tiny little space here. The requirement is, for other, is that there is a force for which we do not know, or in terms of the course, do not care what the source is. For example, earlier on when I had the forces pushing on the box. There was a 5 Newton force pushing on the box. I didn't state what was causing that force. All I said was that it existed. That would be a case of other. So requirement, a force where we do not care. And if you just sort of don't care about anything, you're sort of in that kind of frame of mind, that's not what I mean when I say do not care. I'm talking from a physics analysis point of view. It's irrelevant. Of course, where we do not care / know the source. Typically, other is going to show up in a textbook problem. For the generalized gravitational force, the requirement is 2 masses. To be weight, it's 2 masses when 1 mass is huge and the small mass is near the huge mass. when I'm talking about huge here, I'm talking planet, moon, something of that size. An elephant would be considered a small mass. So pretty much anything that you see on the Earth, other than the Earth itself, would be small.
What do you mean by it's near a huge mass? So like a big-
Near as in, a plane would be considered near.
Okay.
Generally, if you are, the weight actually doesn't change significantly when you're 100 kilometers up, which is officially the edge of space.
Okay.
So, in most of the problems that we'll deal with, where there's ground and you can see the ground.
It's not like a large object and a small object that are like near each other.
Yeah, so I mean, it would not be considered, I would have a small mass, the sun has a huge mass, but I'm not near the sun.
Gotcha.
That would be an example of not near. Near would be something that, if it fell, you wouldn't have to wait too long for it to hit the ground.
Okay.
And I know still vague terminology should be good enough for what we're doing.
Yeah.
And normal force, the requirement is 2 masses touching. Actually, desired relative motion between, throw it up here, between 2 touching masses. Wow. 2 touching masses. All right, dramatic pause for questions.
For tension,
That, I'm trying to figure out where you're pointing.
the second one.
This one?
Yeah.
Taut, rope, chain, etc. String. Yes.
Tyson friction must be between 2 touching masses?
Yeah, for there to be friction, the masses have to be touching.
What are those 2 titles?
Direction with respect to each other, direction with respect to the objects. All right, so when we're dealing with forces, there's some 99+% rules. Actually, there's 100%, close enough to 100% rule. Forces always, not many times we can really say always, come in pairs. And each force in one of those pairs acts on a different object in the opposite direction. So when we start doing force diagrams, we're going to be putting forces down in pairs. The 2 forces that we will draw down, we'll draw 2 arrows. Each arrow will act on a different object, and they will act in the opposite directions. So when I say the direction with respect to each other, that's what I'm referring to, the fact that we have 2 forces that will be in opposite directions. In the case of friction, they will be anti-parallel. They'll be beside each other, acting in opposite directions. And I drew it horizontally, it could be vertically, or, depends on how the objects are oriented. Tension, when I draw it, the two arrows we will draw will point towards each other, which is typically for things that are pulling forces. Other. Other is the case where we actually, even though there are two forces, we actually only draw one. Weight, the two weight objects or gravitational force, those arrows will always point towards each other, whether vertically or horizontally or whatever direction is needed. And normal forces, when I draw that pair, they will always be pointing away from each other. The direction with respect to the objects, they will always be parallel to the surfaces of contact. So I have two objects that are rubbing against each other. The friction forces that we will draw will be parallel to the two surfaces that are touching. Tension along the line of the taut rope, chain, whatever it happens to be pulling. Other is problem dependent. Gravitational force and weight, both of them points toward center of mass of other object. Normal force perpendicular to the surfaces of contact. Yes, Maya.
The tension says along the line of the what?
The taut, tight rope, chain, whatever happens to be pulling. And I do understand all I've done is just spew stuff up on the board. I haven't given much of a context. We're about to do that.
The difference of friction and normal, parallel to the surface of contact and then perpendicular to the surface of contact. I don't know, I think it's perpendicular.
If I've got tape on box, the surfaces of contact are right here. The normal force will be acting perpendicular to that, friction force will be acting parallel to that.
Okay.
All right. Other questions before we start? Force diagrams.
Is that SR combat?
Where are you looking?
The first one, is that next to surface?
Surfaces
Surfaces, what's the?
of
thing?
contact
Oh,
with the straight red mark. All right, let's begin the exciting world of force diagrams. And we're going to start out with box falling. It's the simplest of all the force diagrams. So what I do is I can draw the ground here and draw a box. It is falling. We're ignoring air resistance. Those are there just to sort of indicate some sort of movement. The box is falling. So the first thing I can do is like drawing up the picture of what's happening. You can question my artistic merit, the artistic merit of it, but that's what the attempt was. Next thing I'm going to do, now in this particular case it might seem silly, but strongly recommend that you just get into the habit. The next thing I do is I'm gonna draw the two objects separate where I'm actually gonna draw my forces. So I'm gonna draw my box, I'm gonna draw the ground. Now, when you see the hash marks like this, this indicates something that we're considering to be not moving. Now, it might not have the hash marks, it'll still not be moving, but we're considering it sort of fixed. I'm not worried about the earth spinning. I'm gonna draw up, I'm gonna put up my F-town as my checklist. So for this box falling, the first question is there anything we can eliminate? Any of these forces, the friction, tension, other, weight, or normal, that definitely are not part of this problem.
Tension,
All right, there is no tension, so we can cross that one out,
Friction.
right? Because there's nothing touching.
Normal.
Again, because there's nothing touching. We're down to 2.
other,
Why can we eliminate other?
Did you say can or can't?
Why can we count it out? Why can we get rid of it?
because we don't have. a lot
Because
of-
what?
We don't have a lot of information there.
There's,
No.
the problem did not mention anything else.
Yeah,
It's just, there's a box falling, so other doesn't show up. All right, so all we have to deal with is weight, because I have a huge object, this would be the ground, part of the planet, and here's the mass. So I'm gonna draw my arrows, I'm gonna draw my weight arrow. I know that the 2 arrows point towards each other. This is being pulled towards the earth, so the force on the box is downwards. So I draw an arrow downwards, and I put a little weight right there. And there's a weight right there. The ground is pulling the box downwards, the box is pulling the planet upwards. Now, you don't notice it a whole lot. When you jumped, if I went up on the table and jumped down, I am pulling the earth towards me. But because the mass of the earth is so huge compared to mine, we don't notice its movement. Matter of fact, I've done the calculation. The earth should move, assuming no one on the outside of the earth is doing the same thing. The earth should move basically the width of a nuclear